Hey everyone, in the last video for this week I'm going to talk a little bit about model fit and specifically R-square. So we talked about R-square or the R-square statistic as the proportion of variability in yn in our outcome variable that is explained by the regression. And I want to show you, kind of go step by step through the math to show you why we can interpret it that way. And particularly, we're going to start by partitioning the total sum of squares in our outcome variable into an explained part and into an unexplained part. So the total sum of squares is the sum of deviations between our observed yn and our y bar. So that's basically kind of the variation in our outcome variable that we observe. Okay. And it can be partitioned in the explained sum of squares, that are kind of the part that is explained by the regression, and an unexplained part, which is reflected in the error terms, which is the residual sum of squares, right? And we already kind of talked about in the previous videos about OLS as, or in order to find OLS, we're minimizing the residual sum of squares, right? So that's the deviation between our yn or y hats and the actual yns, right? So we can start by expanding the total sum of squares as follows. The total sum of squares, again, are the deviations between our observed yns and our y bar, the average y, squared, and then summed over all observations from n equals 1 to capital N. And we can expand this again by subtracting and adding a term to kind of that cancels out, but that allows us to rearrange this equation a little bit. We're subtracting y hat n and we're adding y hat n, and again that doesn't change the underlying math. No math is broken. This is still the same equation. We're just subtracting a term and adding a term, similar to this the trick that we used when we derived the OLS estimator. But after we kind of expanded this term with y hat, we can combine this yn minus y hat n as the residual epsilon hat n. Okay, so this becomes epsilon n. That's the deviation between our yn, the observed y, and our predicted y. And we have the second part, y hat n minus y bar n, that still stays the same. Okay. After we have done this, we can basically multiply out this square, and we will treat this as two parts. One is epsilon hat n, and the other one is y hat n minus y bar n. So think of this as one unit, and this is the other unit, right? And so this is again a basic quadratic function. A plus b squared is a squared plus 2ab plus b squared. Okay, so if epsilon hat is a and yn hat minus y bar is b, then we can kind of multiply this out, and we get and then separating the sums as well, we get epsilon hat squared n yn hat minus y bar squared plus 2 epsilon hat n times yn minus y bar. Okay, so this is just applying this basic quadratic formula. Okay. Then after we've done this, we can now plug in our specification or our prediction for yn hat. And remember that given the OLS model, the predicted value of y, or the predicted value yn hat, is equal to alpha hat plus beta hat xn, right? So yn hat in our OLS model is alpha hat plus beta xn. So we're focusing just on the bivariate case here. We could do this similarly for a multivariate case, but it's simpler to just focus on bivariate case here for now, right? So if we plug this in for our y hat, the way we have it down here, we can, in the second part, the first part stays the same, but here now we're plugging in our y hat alpha plus beta hat xn, and we can also plug in our y bar. If you remember, that's equal to alpha hat minus beta hat xn bar, x bar. Okay, so that's also equal to y bar. That's another thing that we showed before. Okay, and we're moving this epsilon hat to the end. So that's basically all we did here. After we have done this, we can pull a couple of things out of this sum. Particularly, we will move this beta hat out. Alpha hat minus alpha hat, of course, cancels out. So we're left with beta hat xn minus beta hat x bar. We pull out the beta hat out of this product and put it in front of the sum to get 2 times beta hat xn minus x bar times epsilon hat n. Okay, the stuff in the front still stays the same. And now we can rearrange this a little bit further. We can multiply out this product xn minus x bar times epsilon hat n, and then separate those sums. And so what we're left with is the sum from n equals 1 through n of xn times epsilon hat n minus, and the x bar doesn't have an indicator for it's constant across n, right? Obviously it doesn't have a subscript, so we can pull it also in front of that sum. So we have x bar times n equals 1 through n, the sum of epsilon hat n. Okay. Now consider again the two first order conditions for OLS in the bivariate case. We had the first order condition yn minus alpha hat minus beta hat xn being equal to 0. That was the first order condition for alpha, and we had the first order condition with for beta, right? And so these yn minus alpha hat minus beta hat xn that's of course our epsilon hat, and this part here is also our epsilon hat, right? So these are the first order conditions that we started with OLS. The fact that these two hold in the OLS case for alpha and for beta to get our OLS estimates, right? This was based on the minimizing the sum of squared residuals, taking the first derivative, setting it equal to 0. That implies essentially, if we look back at this equation, xn epsilon hat minus x bar sum epsilon n, the fact that for the OLS estimator that these two equations hold, that this is equal to 0 and that is equal to 0, that implies basically that this term 2 times beta hat that we kind of extracted previously, xn epsilon hat n minus x bar epsilon hat n, that is equal to 0, because we see here this is equal to 0, that's basically the first part here, and this is equal to 0, that's the second part here. So this is 0 minus 0, so this all cancels out, right? So that means that our decomposition that we had previously of our total sum of squares, this second part here, given that with OLS these two first order conditions in the bivariate case hold, this part cancels out. This is equal to 0, which means our yn minus y bar, which is the total sum of squares that we started with, can be kind of expressed alternatively as the sum of the squared residuals plus the squared deviations between y hat and y bar, which in other words means that the total sum of squares, that's what we started with, is equal to the sum of the residual sum of squares plus the explained sum of squares, so the deviation between our y hat and our y bar. Okay. Now that we have shown that the total sum of squares is equal to the residual sum of squares plus the explained sum of squares, we can basically define r squared based on this decomposition, right? So if we define r squared as the explained sum of squares divided by the total sum of squares, so how much is explained by the model divided by the total variation in the outcome, we can, instead of writing these explained sum of squares, we can basically replace this by the total sum of squares minus the residual sum of squares by just, this equation we have shown already. If we put the residual sum of squares on the other side by subtracting a residual sum of squares on both sides, we have basically ESS equal TSS minus RSS. So we plug this in here, and so we're left with TSS minus RSS, total sum of squares minus residual sum of squares divided by total sum of squares. We can separate this this fraction, of course, total sum of squares divided by total sum of squares minus RSS divided by TSS, and of course total sum of squares cancels out, so it's 1 minus RSS divided by TSS. And now going back again, what are the residual sum of squares and the total sum of squares? Those are just the squared residuals summed, of course, and yn minus y bar squared. So this is kind of the derivation of how we get to r squared being equal to 1 minus residual sum of squares divided by total sum of squares, or 1 minus epsilon square, the sum over all observations, divided by yn minus y bar squared, summed over all observations. And that's the specification that is shown in the book, but we didn't really go through how we get to that specific specification. So furthermore, when we look at the residual sum of squares, as I said, we can define them as the explained sum of squares divided by the total sum of squares. If we plug in the explained sum of squares up here and the total sum of squares, we can also plug in our y hat, or plug in alpha hat plus beta hat xn for our y hat in the numerator. So we have alpha hat plus beta hat xn minus alpha hat minus beta hat x bar, because this is y bar, of course. And so if we plug this in, we can further kind of simplify this, because alpha hat cancels out and we're left with this expression. We can then basically kind of pull out the beta hat square and pull that in front of that sum. So we're left with beta hat square sum xn minus x bar squared. And then based on that, if you notice that beta hat square, or the remaining part of this fraction, this sum xn minus x bar, if we just divide by 1 over n here in the numerator as well as in the denominator by 1 over n, these are equal to the sample the sample variance of x divided by the sample variance of y. This is just this expression down here divided by n is the sample variance of y. This expression right here divided by n is the sample variance of x. So this is equal to beta hat square times sample variance of x square, sample variance of x divided by sample variance of y. And in the textbook, I think, yeah, this was in equation 4.8 in chapter 4. We have also shown that beta is equal to a reweighted, or the in the bivariate case, is equal to the the correlation coefficient between x and y, weighted by the standard deviation of y divided by the standard deviation of x, right? So if we plug in this beta, this correlation between x and y times sy divided by sx, in here for our beta hat, what we're ending up with is this expression squared times sx, standard deviation of x squared divided by standard deviation of y squared, and we see the sy and sy squared and the sx squared and the sx squared here all cancel each other out. So what we show by kind of plugging this in is that r squared in the bivariate case is equal to the square of the correlation coefficient between x and y. So the r square statistic is not only cannot only be interpreted as the proportion of variance that is explained by our model. In the bivariate case, the r square statistic is the square of the correlation in the case of simple regression. And of course, this implies that the r square statistic can take values between 0 and 1, where the value of 1 would imply a perfect fit of the data to the regression line. So all the variation in y is explained by x, and a value of 0 would imply that xn has no value in predicting yn. Right? So I hope this gives you a little bit more kind of a deeper understanding of r square and model fit in the context of the linear regression framework. All right, that's all I have for you for this week. I'm looking forward to our next Q&A session next week.